Hello. In this video, I want to look at the graph of a rational function, show you how we'll go through a full analysis to sketch the graph. So we'll take this function, f of x is equal to x times x minus 2 divided by x plus 3 squared. And this function happens to be presented in graphing mode, which is just fine. Let's set up the axis over here, and we'll use this axis to sketch the graph of our function. Again, always label your axes. We've got x and f of x as well. Well, the easiest point, I think, to find on a graph would be the y-intercept. And if we let x equal 0, we've got a y-intercept at 0. We can also check for x-intercepts. Now remember, in a rational function, in order for that function to be 0, the numerator has to be 0. And we've got this numerator here in factored form. We can see that if x is 0 or if x is 2, there's an x-intercept. So the origin is our x-intercept and our y-intercept. We've got an additional x-intercept at 2, 0. Next, being that this is a rational function, we look for asymptotes. Notice that the degree in the numerator, were I to multiply, would be x squared. The degree would be 2. In the denominator, the degree would be 2. So we know there's a horizontal asymptote, y equals 1. Horizontal asymptote, y equals 1. Since the function's undefined at -3, I cannot remove that problem. We've got a vertical asymptote at x equals -3. Alrighty, let's add this information to our graph. Let's add this information to our graph. Horizontal asymptote, y equals 1. Just increment these axes a bit here. You always want to increment your axes so your reader knows your scale. We've got a horizontal asymptote, y equals 1. We've got a vertical asymptote, x equals -3. We have a y-intercept at the origin and an x-intercept at 2. This makes for a very interesting function. Now, since we know that the function will either be above this horizontal asymptote or below, I see no other x-intercepts. I really believe the function's going to be living in here. Similarly, I think, left to be seen, I think maybe it's going to be living in here, although this is a bit curious. So now we want to set up our if table to take a look at our function. Now, we have 1, 2, 3 critical points along the x-axis, and they divide this axis into 1, 2, 3, 4 intervals. So let's list those intervals here. 1, 2, 3, and 4. And I've got x is less than -3. -3 is less than x is less than 0. 0 is less than x is less than 2. And x is greater than 2. So again, these are my 4 intervals along the x-axis. And for our factors, I've got a factor of x, a factor of x minus 2, 2 factors of x plus 3, and so I've listed my factors. Now I will determine whether the function is positive or negative along each of these intervals. All right, x, negative, negative, positive, positive. X minus 2, I'm subtracting 2, negative, 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 positive. X plus 3 is squared, always positive. All righty, 2 negatives and a positive, the function is positive. 1 negative, it's negative, and 3 positives, it's positive. All righty, this if table tells me my function is positive. So I've got a piece of the function like so, approaching these asymptotes. Now this is interesting. The function is positive from -3 to 0. It's negative from 0 to 2. And it's positive again, greater than 2. So I picked this rational function for my example because of its interesting behavior close to 0. You see, this function has to approach this vertical asymptote. It's got to go here. So this function's got to be coming down like so, hitting a low, coming back up, and then it's approaching this horizontal asymptote. So here's a sketch of this rational function. Again, I selected it because of the interesting behavior of the function near the origin. You see, with the case of horizontal asymptotes, the function approaches those asymptotes when x is large enough toward positive or toward negative infinity, you see. So things can happen close to the origin. And in this particular rational function, we see that it's crossing from positive values of y. It's coming down, hitting the x-axis at 0, coming down, bottoming up, then coming up again. Notice then that this function does indeed have an absolute minimum value somewhere in here. Somewhere in here there's an absolute minimum value. We could find that because we know at that absolute minimum the tangent to this function would be horizontal. So we could take our difference quotient, although that would be a good exercise in extra credit to take that difference quotient, but we could find it, find the values where that difference quotient is 0, and that will give us the x value where this function has an absolute minimum. We could take that value of x, plug it into the function, and find that minimum value. When you take calculus, you'll take the derivative of this function, set that derivative equal to 0, and sure enough, you'll find that location. Notice the function has no absolute maximum. It has no relative maximum either. And in terms of concavity, the function is concave up, concave down. Notice the function is increasing, the function is decreasing, and the function is increasing. It's a great rational function. It displays a lot of the characteristics of rational functions. So, once again, I hope you find the video and explanation helpful as you pursue your study of pre-calculus. All the best for your success.